All right, so we've gone through these questions pretty thoroughly, and if we look at number 7, it says, which of the following is generally true of K strategist species as compared to R strategists? So to look at K and R strategists as far as reproductive strategies, and that's what they mean is reproductive strategies, right? There's two types. You have a K, which is species experience, where you have focused on few births in a given year, and a lot of resources are dedicated to those few births, versus the R strategist. And why do they say K strategist? Because you'll notice the K stays around the carrying capacity, so you have kind of level population. So things like elephants, things like rhinoceros, things like humans, we're K species reproductive strategy, in the sense that even though we have a high population, we tend to have only a few babies at a given moment, at a given reproductive cycle. Where you have R strategists, they focus on the exponential growth curve, the early part of this logistic curve, and they focus on having a lot of progeny all at once. At every reproductive cycle, they might produce tens of thousands in the case of roaches, right? So that's a reproductive strategy that's either K or R, and R means it's here at the exponential growth phase, so there are a lot of babies, all right? Where K, you only have a few per reproductive cycle. So to take a look a little better at a survivorship curve, and kind of how this curve works out in the survivorship of individuals in a population. Let's again look at that rhinoceros, and this time let's compare them to birds and fish. So when we look at survival of K versus R, we have these rhinoceros at the K species. They tend to live about. You'll notice that all three species live about the same age, but those that reproduce using the R reproductive strategy, like fish, a lot of them die early on. But once they have the ones that survive that early culling, right, they last a long time. In fact, last as long as, in some cases, obviously, different species vary, but they last about as long as rhinoceros. Whereas humans and rhinoceros follow the same curve, what you see is we last a fairly long time, and as we get old, whatever old means, you notice there's no numbers on age. And once we get near the old age, we drop off very quickly. Where things like birds, they have a fairly constant loss rate. So they don't lose a lot when they're young. They don't lose a lot when they're old, as we do, as a rhinoceros do. But they kind of stay they're in between. They're in the middle. However, when we're talking about K and R strategies of reproduction, again, you're talking about whether individual species decides to have only a couple babies at a time in a reproductive cycle, or do they have tens of thousands at a reproductive cycle. So two different strategies, both fairly successful. You lose a lot of the young using the R strategy, but the ones that make into adulthood stay alive long enough to die of old age, whatever old age is. For a roach, it might be a year, I'm not sure. But, for a rhinoceros, it might be 60 years old or 40 years old. Again, I'm not sure what the lifespan of a rhinoceros is, but for humans, it's increasing all the time, but about 70 years old now, depending on what country you live in. So when you're looking at the question, which of the following is generally true of K strategists as compared to R strategists, you have to look at some of the qualities of R versus K strategy. So in an R strategy, again, you have many offspring, and in K strategy, you have few. And that's the biggest difference between the two. Parental care, because you have many, there's less of them, less parental care. So the fish, when they lay their eggs and they're fertilized, the fish go away, and the young take care of themselves the same goes with roaches. In case strategy, the parental care, there's a lot more, and again, it depends on the species, but more versus our strategists. Our strategy mortality rate's high, especially in the young. In case strategy, the mortality rate's low in the young. Body size, our strategists tend to be small because they have so many babies. They can't afford to make them all fairly large. Case strategies tend to be large. We're considered large. Our strategists reproduction once usually. Case strategists have more than one. They reproduce more than once within their lifetime. Favorite environment. Our strategy tends to be taken up when this environment's unstable. So you can imagine the life of a roach. Today there's wallpaper. Today no one's lifting up the curtain. They're alive. They have a place to live. The next day somebody lifts up a curtain and starts vacuuming up. So an unstable population, you can again imagine the fish laying their eggs, various weather conditions, various, low tide, high tide, predator species, very unstable environment to live in. So their strategy actually works out pretty good for them. If they have a lot of young, a lot of them are going to die, but there'll be enough that some will survive and the species will go on. Case strategists are called climax species, right? Or I'm sorry, they tend to live in stable environments. They tend to, a lot more stable than our strategists tend to be found in. Our strategists tend to be pioneer species, so they go in. The roach is a perfect example, right? So they'll find niches anywhere they can find space, right? In between the wallpaper and the wall, in the walls, in the floorboards, in the cupboards, you name it, they're going to find a place to expand their territory. And so they're very much a pioneer species, and they start small colonies, and they have a lot of babies, and a lot of them die, but enough survive to go on to the next species and the next generation. So this type of species, our strategy works well for this kind of species. With a case strategy, you're looking at something that's a climax species. So it's not going to, it has an established environment, usually a territory. There are very few things hunting it, so they're more stable. That's hence the stability, right? So there's very few things hunting it. Their environment's relatively stable. So this climax species, we tend to have this case strategy with us. And population size is very variable. So, roaches could have tens of thousands when no one's living in the house. Someone comes in and fumigates, down goes that population to virtually zero, and they have to start over again. Where a case strategy has a fairly stable population size. It goes up and down like all populations, but it stays within a normal range. And remember, all these change depending on the environment. This is just looking at how these strategies over time, over hundreds or even thousands of years, that have worked for these various organisms or species. All right, so now let's go ahead and take a look at number 7 again. So number 7 says, which of the following is generally true of case strategist species as compared to our strategist species? So they reach sexual maturity earlier. K's reach sexual maturity earlier. That doesn't make sense, right? Our species, they're going to remember their qualities. You're going to be talking about onset of maturity is early. First of all, that tells you the answer there. But if you think about a roach, a mouse, these things have to come to maturity early so they can have babies, because their lifetimes tend to be much shorter, right? So sexual maturity early doesn't make any sense and would be wrong. They have more young. Well, that's true. Our strategy, I should say, this is wrong that K is earlier, right? And so B says that K has more young. Well, that's not true. It's R, right? That's the whole point. That's the biggest characteristic difference. and drives all the rest of these. They are more likely to be invasive, to be an invasive species. Well, we know that's not true, right? So what do I mean by that, by invasive? Hopefully you understand that means that a species is going to be found, is going to come from outside its niche, from outside where it normally, and it's going to be a pioneer, right? It's going to go into places that it hasn't been before. Well, we know from this list here that our strategists are indeed the pioneer species. And just think of the roach. Anytime you think of an R strategist, just think of the roach. The roach goes and finds new habitats all the time. They're chased. Mice, another great example. People are constantly trying to chase down mice and kill them. And so they have to be a pioneer species or invasive, and they can therefore turn into an invasive species early. A rhinoceros, difficult for a rhinoceros to become an invasive species. I mean, think about their mobility. Humans can be, right? So we are very much an invasive species, I suppose. But because we're at the top of the food chain, I'm not sure. We'd have to think about humans being invasive species. But in any case, they're more likely to be an invasive species. Obviously, R is going to be the more likely of the invasive species because they have so many young, because they have early onset maturity, because they're small organisms that can move quickly. Therefore, it's much easier for them to be found in, or can find niches in order to compete. They require less parental care, so they can spread faster. They have variable population size, so that doesn't really impact the idea of it being invasive. But it's used to having an unstable environment, and it's used to adapting. So our strategists tend to be these invasive or pioneer species. Let's look at E. Before we go, we know the answer is D. Their population cycles are more rapid. Well, we know R has a population cycle that's more rapid. I mean, that's the whole point, right? They have more babies. They sexually mature faster. Although they tend to only reproduce once themselves, their offspring can be ready to reproduce very quickly. So E is wrong. And finally, so the answer is obviously D. And K do have longer lifespans, right? So because there's this concept that these organisms invest so much in one or two, that energy is to make sure that those one or two reach a longer lifespan. Now, or reach their maturity, the end of their lives. So if we take a look at these three species, and you just notice that they all reach their end of their lives, that what you're looking at here is not the same age, right? A fish doesn't live as long as a rhinoceros, so that it might, depending on the species. The point is that of all that were born, of 100% that were born, most of the rhinoceros die at the end, where of 100% that are born, most of the fish die early on in their lifespan. Nothing here tells you anything about lifespan. So don't confuse those two concepts. All right, so let's move on to the next one then. The next question, 8, says it has recently been estimated that the growth in world population has slowed in the past decade. Despite this trend, environmentalists remain concerned about the environmental impact of world population, principally because we've slowed our growth rate for all the reasons we've already talked about. Why are environmentalists then still worried? Well, let's go through the wrong answers and then let's focus on the right ones. On the right one, people are living longer in developed nations, putting strain on economies on those of those countries. Well, even though that's true, we know that's true. That's not really the concern. The concern of the environmentalists, it is putting a strain on the economies of those countries, and people do have to decide how we're going to take care of our old. But that's not really the primary concern of environmentalists as far as the environmental impact of that population. So now C, as life expectancy is still decreasing in Africa due to AIDS. I'm not sure if that's true. I'm sure at least in part it's true. But again, as far as environmentalists is concerned, the environmental impact of humans on the environment, you would think that would be, I don't want to call it a positive, but it would have it would have a positive impact on the environment if you had less individuals to use up the resources, right, to negatively impact the environment. There's also some negatives due to that, right? So the political, the social instability that is created by having this higher death rate does also cause a greater environmental harm than you might have if you had a more stable social environment. So C does have an impact both positively and negatively to the environment, but really what you have to concern yourself with is that it's not the best answer. So the standard of living is poor in many developing countries, leading to a great deal of deprivation and suffering. This also is very true. So that's three that are very true, and it's not the main impact on the environment. And so what are we concerned with when we're talking about the decreasing of the population, the world population? And E, fertility is falling due to exposure to endocrine disruptors released into the environment. That is happening in different degrees in different places of the world. We've seen it in alligators, we've seen it in frogs, and there's been some recorded evidence in human populations. In fact, that whole BPA, the BPA scare, and the taking the BPA out of our plastics is due to this endocrine disruptor issue. The question, though, is if we look at the best answers, the standard of living is increasing in many developing countries. That's true. All right. And leading to an increased per capita use of natural resources. So for this answer, you need to think of China and India. All right. China and India is their standard of living is increased. They have more phones and more cars, and they're no longer they're increasing their infrastructure. They're building cities and they're building dams. The Three Gorges Dam was built about 10 years ago. Maybe it's even 15 now, where they've dammed up one of the Yangtze River, one of the biggest rivers in the world. They've dammed it up and have stopped flooding in many areas. There's just a lot of improvements to daily life of your average Chinese citizen or Indian citizen, and that's great. But the problem with, as far as environmentally, is that as you get, as people in these developed countries start to move to the lifestyle that Americans have been used to. So when you're moving from walking and maybe horses, or maybe even one car, one truck per village, to 2.5 cars per village, per person. When you start moving from one phone in the village, to everybody having their own cell phone. When you start to open up malls and department stores in places where there used to be just dirt road access, now you have a highway coming in. These are going to start impacting the environment negatively, and that's what an environmentalist is going to be concerned with. As we increase the quality of living for the larger portion of the population, there's going to be that much more of an impact on the environment, and that's a real issue. that we have to deal with. And we can do both, right? Technology is going to help us do both. It's going to be difficult. It's going to be a struggle, but it's possible. If you think about, solar power can increase the standard of living for everyone involved and still have a relatively small, a much smaller impact on the environment than, let's say, coal or gasoline would. So as an environmentalist, you got to think, could technology end up helping us improve the negative impacts on the environment, even though we're increasing the standard of living of these individuals in these countries, in these developing worlds? Can we do both? I think we can. So 9 factors contributing to the rise of world hunger include all the following except unequal distribution of available food supplies. Well, that's obvious, right? That's obvious. It should be. In fact, even when the UN tries to distribute foods in war-torn nations, often the various sections, the various sects that are warring will take over that food and confiscate it. It's happening in Syria. It's happened in Africa. It's happened in Europe. Loss of or decline of arable land. For sure, we've lost a lot of our land, at least the land that can be plowed and where we can plant our foods. How have we lost that land that can be plowed and grow foods? Drought, sea level rise, building of cities, right? Building highways, populations, pollution. All these things have decreased the amount of land that we can actually farm. So that's a real issue for our world. Increasing rate of population growth. Well, it's kind of, you might want to say no because of this number 8 that says the population has slowed, but that's the world population. Individual areas, we still have increased rates of population growth. So in those areas where we still have in those areas where we still have a lot of population growth, and it's usually those pre-industrial areas where we've sent in medics and medicine from more developed countries to stop the disease and death that's occurring. The population's bulging, but they don't have the as they haven't gone through the transitional phase yet. They haven't gone into the post-industrial and post-industrial phase of their society, so they haven't realized that they have to control the population. So what we're looking at sea, there's numerous countries around the world where you have this population growth, even though you have poor services, poor resources. In places like Haiti, places like some places in Africa, you have there's numerous places where population growth is still relatively high in especially local population growth, but resources are poor. Increasing poverty in developing countries. Again, we have this, and we should look at South America as well as some examples of this increased poverty. Yes, that's true. And that increased poverty, of course, it brings with it hunger. So this rise of world hunger around, it has to do with the fact that these countries are poor. They don't have enough. They're not able to grow food on the lands that are available to them for the various reasons that we discussed a second ago. There's an unequal distribution of available food supplies. There's one here that's missing as an important one, which is the availability of potable water. That's a big one. It's probably the biggest one today. So you should see how old the question is. So water is the access to water is a real big issue. So having land, not having arable land, right? Not having the land to be able to grow food in, arable. That's what arable means, to till food. Today we know we're missing also this big one, and it's probably the biggest one in the world, and that's not having enough water to for the population, and then again for agriculture. As we discussed earlier, it's even happening in California, which is, crazy really to some of us, even though it's been happening for a while. So increasing consumption of vegetable protein in place of meat protein will not increase world hunger. I know some of you might say yes, but E is absolutely the right choice. And you can see that the reason I spent so much time on A, B, C, and D, even though E is obviously the answer, I think it's important, guys, that you think about all these wrong answers and think about what it means. You can see from these three research pieces that I gave you, right, that looking at K&R Strategists, even if you knew what K&R Strategist was offhand, I think by looking at the wrong ones, you can see all that you learn, or you relearn a lot of the qualities that each of the strategists actually have and don't have. So it's important to look at these wrong ones on these practice tests. All right, so let's look at this, at reading this graph. Blank represents the maximum number of individuals that can be supported in a particular ecosystem on a long-term basis, E. And the answer is E. That's this one. That's your carrying capacity. And that's right out of chapter 4 or chapter 3 as well. This is dotted line. That's remember, the carrying capacity is the ability of the land to sustain a certain population. It can't sustain it after a certain population, so the population starts to die out. As you can see here, let me see if I can make this a smaller dot. You can see here the population goes above the carrying capacity, but because of starvation or because of lack of resources, the population starts to die off or starts to decrease. But once it goes below the carrying capacity, there's excess resources, so the population starts to increase again, and it just keeps having this sinusoidal curve, this up and down movement around the carrying capacity. And for most of you from ninth grade, I know you probably remember, and if you don't, you can go back and look at this idea of homeostasis. And really, homeostasis, or a dynamic equilibrium, we have this line where the population is going to stay around, but it doesn't stay at that line. The population doesn't stay at E. It goes above and below it, but it stays around E, and we call that a carrying capacity. All right, so that's the maximum number that the land can sustain. All right, 11 represents the biotic potential of a species A. The answer is A. And so what we're talking about is the biotic potential is what is the potential for this particular species to, what is the potential of this specific species population given a certain amount of time with unlimited resources in this kind of fantasy world where there's no limit to the resources. We know there's limits, right? We'll run out of land and space and water, and there'll be, as we discussed earlier, arable land and all kinds of things. They're gonna restrict the amount of the population size of any species. But no matter what, there's this idea that what is the population that, if there was no limitation, could we calculate what kind of population that a specific species could have? And that's the potential of that species. And here it is, that's A. As you see, E is the actual population size. It's going to happen. So this is what it really looks like. And this is what it could be if it had unlimited resources. All right, 12 represents the growth of a population predicted by a logistic model, C. So C is looking at a logistic model. So if we're looking, and you could actually look at it here as well. This is a more logistic, very, very clearly logistic curve. But what happens here is this one goes up and down. So the logistic model C, I want to explain what I'm saying. If we extended this line out here, we would see it would kind of flow up, and it comes off, and then it starts to decrease. and it would have kind of, if this line just kept going across and reached this limit and didn't decrease or increase or decrease, we'd call that logistic. And in fact, if we draw a line from here, if I drew a line here and here, it would look identical to this line here and here. And so in that portion of the lines, we would call that logistic. But given these choices, A, B, C, and D, A, B, C, D, and E, the logistic curve is C. It's the most logistic of the curves that we see on this graph. So this is the logistic model would predict it, and obviously this is the exponential model is represented by A, or the biotic potential. And you should note, just like I did with the logistic curve, we can cut out a piece of this logistic curve and here, and we can see that the exponential curve, which is represented by the biotic potential A, and the actual data from the population, what actually happens, we can see that this portion of this curve matches exactly with A. So it's interesting. Moving on, and that's important because that actually came up a couple times in some of the problems you've seen, and it'll come up again. Understanding these curves and realizing that the various portions are very similar because the qualities or the environment in those portions are very similar. So for instance, let's take a look at this dark line B. Why is it that the potential before it reaches the carrying capacity, this line looks like it's going to be exponential? In other words, it's going to reach its the population of the species is going to reach its potential. The reason is that the environment is not unlimited in resources, and as it reaches that limit, the population starts to decrease. Then the question is, why isn't it more logistic? Well, the particular species had a larger than predicted birth rate, or the resources were more plentiful, and so you had a larger increase originally than you would have expected in the logistic curve. All right, so let's move on. Number 12. All right, so we said the answer that. And 13, if a city population is 10,000, experienced 100 births, 40 deaths, 10 immigrants, 30 immigrants the course of a year, what is its annual percentage growth rate? Well, let's take a look at the math. So if we go ahead and put the 100 births plus the 10 immigrants are what's coming into the population, and we subtract 40 deaths plus 30 immigrants, those are the ones that are leaving the population, right? These are leaving, these are coming in, this is out, this is total, and that gives us the annual growth rate, and that turns out to be here at 0.4%. It's just in minus out divided by total. But you have to consider not just the deaths, because there's more than one way to leave a population. You could also leave it voluntarily. And the same thing with births. Here come the involuntary coming in, and then there's a voluntary coming in as well, the immigrants. All right, so that's 0.4%, 0.4 growth rate. All right, let's move on to the next set of problems. So let's take a look at this structure before we try to answer number 14. This is from your notes. And if we take a look at these growth structures, you'll notice that populations are growing very rapidly. Again, we're talking probably pre-industrial. You have a lot of young, not a lot of old, not a lot in the middle. Expanding slowly, you still have more young than you do have middle or old, but notice that your widths are not as big a difference, right? A stable population, you kind of have the middle and the young are equaling out. You have as many young middle-aged people as you do young people. And in populations that are declining, your older population, middle to older, is actually larger than your young. So Italy, Germany, Bulgaria, and United States is probably around here in the stable, expanding slowly. And the thing is with America, even though we have a great, even though our population we're in stage 4, where we're a mature country, post-industrial, right? The issue is we have a large immigration, so that expands our population, but our native-born population has decreased so much that our growth rate is still relatively stable. So it's really, really interesting, and part of what's driving our politics today. So if you take a look at this distribution, right, age distribution, which was this most like? If you notice that if we drew a line straight up, you do have less older than young, but the middle-aged and young are pretty much equal, and it's almost a rectangle, right? So here you'll notice that in the declining you have a smaller end, right? All right, so here you see that there's a more triangular base to it, and this is an extreme triangle or even an arrowhead. You can see why someone would actually label this population stable, right? Or the population is almost slow or no population growth. All right, so it would be very much in the stable range, where the United States is probably a little bit more of expanding slowly, even though a lot of us are only having 2 point some odd children each. The issue is that we have a lot of immigration, so our young actually do outnumber our old. So we do have an expanding population. All right, so let's move on. But before we do, I'd like to go over these other answers and say, is experiencing rapid growth? Again, if we were experiencing rapid growth, there'd be a large young, 0 to 14, right? So there'd be a big population boom. A lot of the middle-aged people would be having babies. So that's not the case here, right? So we can knock out A. C says experiencing high death rates. High death rates where? I mean, in the older population, presumably. Well, it doesn't seem to be happening. We seem to have not a lot of this. If we were having a lot of death rates, we'd expect kind of see something like this, right? Where somewhere, or even something where you have, I just don't know what that would look like, just experiencing high death rates without mentioning an age group. You'd have to assume that it would be the older population, could be the middle-aged population if there's a war or something like that. So you might get something that looks like that, like an hourglass. As the old stay home and the very young are still home, the middle-aged people go off to war and die. So you might have something like that after a war, during a war. So I'm not sure, but it doesn't seem to be the case here with this particular age distribution. As you see, the age of the population is pretty much stable. No one group is dying off much faster than any other. Has 40% of the population under age 15. Has 40% of the population under age 15. Well, 40 is close to half, right? 40 is close to 50. This would be under age 15. So I don't see that more than half the population, or close to half the population, is 15, right? 15 or younger. So I don't see that. I don't see the dark rectangles increasing either for females or males much more than the rest. So I don't think that's obvious. I think it's obvious to me anyways that this is not the case. Because if it was, then I would expect to see kind of some crazy thing like this. Right? Where you have a big part of the population, 40% is a big part, would be under the age of 14, and that's not what we see. Is a less developed country. Now that's an interesting choice. Remember, in less developed countries, what we'd expect to see, and let's go ahead and go back and look at that, those standard age distributions. Let's quickly look at developed countries versus developing countries. This is from your notes, and this is from 2006. If we take a look at it, you see that in a developed country, you have more of the middle population. The older people are dying, and they're usually at an older age. You see the average of death is probably closer to 70 here. And you see that you see that the young are smaller than the middle-aged. So this is a developed country. In a developing country, what you see is a lot of young, very young. Most of the young are 15. In fact, there's a 32%. And remember, I drew out, like, if it was 40%, it'd be a big block here. So this is 32%, 7%, or 8% below what we were looking at the problem at D. And you still get this like arrowhead shape, as I showed you earlier, in a developing country where you have a lot of young, strong middle aged, but the older people are much harder to find. And the age, look at the age, 60, 85, 80, 70, small, but the proportion of the old to the middle is much smaller than you might find in a developed country. So then, again, this doesn't match a less developed country. A less developed country would look more like this arrowhead and less like this rectangle. All right, let's take a look at this calculation, which seems difficult until you start to use scientific notation. So when we take a look at this and we see we make the calculations, we see that 6.10 times 10 to the 9th, which is this big complicated number, right? How did I get that? Well, all I did was I took the decimal place and I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 times. That's where I got that 9. This is called scientific notation. You've learned it several times in high school. And here is another decimal, which you say 0.0135. We just move it twice, 1, 2, so that this number has the same significant digits as this one. So 6.10, 1.35. And you'll note that the answer has the same significant digits, 8.23. Now they rounded off to 8, which is fine. And the reason they rounded off to 8 is they don't expect you to do this calculation. They don't need you to do this part. What they're looking for, because you can see all their answer choices are 8. So what this 6.10 times 1.35 equals really won't impact your answer, or really shouldn't. So now, whenever you multiply two numbers that are in scientific notation, you're either going to add the exponents or you can subtract them. When you're multiplying, you're adding. Well, you're just always adding. You're adding. In this case, I'm adding a negative number. When you add a negative number, you subtract. So it's 9 minus 2 is 7. And that's how you get this 7. You don't need to do this big long calculation and start to move decimals around and multiply and keep multiplying and moving down numbers until you get this really large number of 8.23 times 10 to the 7th. All you need to do is know how to do it, how to write numbers in scientific notation, and understand that when you're multiplying, you're adding the numbers. When you're dividing, you're subtracting the numbers. These exponents are subtracted when they're being divided, and they're added when they're being multiplied. So just know that. In this case, we're multiplying, so we're adding 9 plus negative 2, which is 7. And that's how we get this answer quickly without having to do any long division or long multiplication. So So the next one is a doubling time problem, and it's really easy because they give you 5%, and you know you're just taking 70, you're dividing by 5, and that's the number of years. All right, so it's going to be 14 years. And so it's going to be 14 years, but the one that's closest to it, because they actually ask you, is closest to what? 15 years. So there's your answer. I don't think this takes any more discussion since we've covered doubling time in a previous video, and we've gone over it in several different ways. Okay, number 17 is a real interesting problem on a couple things, for a couple reasons. So it says, Earth's human population last century has been dramatic, right? The increase, it says increase. So this is one of the key points that lets you get the right answer. And so which of the following is two major contributors to this increase? And the first one is new methods of agriculture and identification of new crops. So this was important. This is important, okay? So remember, multiple choices, choosing the best answer. So these are kind of important aspects of growing. The next one is going to be even more important, and there is a connection between A and B, and we'll discuss what that connection is in a second. So C is increased immigration and emigration and decreased warfare. We're talking about the Earth's human population. I thought this was cute. How are you? Are we leaving the planet? Are we having aliens coming in? Are aliens from outer space increasing our population? Because that's the only way this portion of C could possibly be right. So C's off base, completely off base. D, the new methods of birth control and decreased warfare. Decreased warfare could increase population, but birth control, first of all, we should know historically that we have not decreased. In the last century, we have not decreased warfare. In fact, we've found bigger and better ways of killing people. So warfare has not decreased, and in fact has become more efficient at it. We've become more efficient at it. We've had less wars, but they're much more violent. All right. In any case, the new methods of birth control, that would decrease the population. That wouldn't increase it. So D is wrong. And increase education for women and develop new pesticides. Well, increased education for women, you should know, hopefully you know by now, is going to decrease the population size. Because as we educate women around the world, women start to realize that having fewer babies makes their lives better, makes their ability to take care of that child better. So in most developed countries, women have much fewer children than in developing countries. So in any case, in the last century, women have had actually less. As we've educated women, that's decreased the population in those particular areas. So really, we're just stuck with A and B. And sure, that new methods of agriculture and identification of new crops are important, but it was due to the Industrial Revolution and modern medicine had the biggest impact on the human population in the last century. And in fact, it was in the Industrial Revolution that allowed us to perform some of those new agricultural methods. The invention of the combine, the invention of the tractor, they made agriculture much more productive. So that was part of the Industrial Revolution. So even though it's agriculture, you shouldn't just think of the Industrial Revolution as just factories. The Industrial Revolution allowed us to produce a lot of things. And some of those things ended up in the rural areas helping farmers. All right, I'm moving on to 18. Okay, so the answer is obviously E, and it's greater in countries. And if you think about it, if you think about what replacement level fertility is, remember it means the number of babies that an individual woman, number of babies a woman would need to have to replace herself and partner. So in countries where you have a high infant mortality rate, and remember that there's some factors you have to think about when you're talking about this number, and you had to calculate it in class if you remember correctly. You have to remember that when any individual female in a population, when we're talking about replacing that population, if out of any number of females in that population, there's going to be some that will not procreate because they cannot. There will be some that will not procreate because they choose not to. And so it falls upon the two that are left, or those that are left, to have the number of babies required to replace that population. And of course, in part of that calculation are the females that have the children but those children die. And when the mortality rate is high, that means that the average number of babies per woman must increase. In order to replace those children that have died due to some infant mortality rate, whether it be Zika virus or it be some drug epidemic or whatever the case may be. Any country that has a high infant mortality rate, and it's not just birth, right? It's anytime the infant means birth or before it's an actual child, so as they're learning to walk. So these infants, the high mortality rates, means that these females have to replace those individuals, the ones that can reproduce and that are able to do it without losing them. So the average number of live births have to increase, right? And per woman, the average number of babies that each woman has to increase. All right, so knowing that, let's take a look at the wrong answers and try to figure out why they're wrong. It equals the average number of children a woman will give birth to during her childbearing years. That's total fertility, right? That's total fertility. And the next one equals the annual number of births per 1,000 in a population. And that's that crude. There's that crude fertility. And the next one, it equals the natural increase in the population in 1 year. Well, isn't that just population growth, right? And the next is found by subtracting the number of emigrants from the number of immigrants in 1 year. This has nothing to do with fertility, right? That does feed into growth rate, but not fertility. So that's why these four are wrong, and why this one is the right answer. All right, I hope that helped you understand all these questions and answers. A list along with the other videos should be a complete description of everything that we need for to get you ready for your exams. It's concerning populations. Also, please reference the notes I sent you through Jupiter Grades last night. All right, have a good one.